Hi everyone, I'm Gal, and today I'm going to talk about serverless distributed systems and why distributed tracing is a key component in understanding this serverless environment. So let's first talk about distributed systems. In recent years, we've seen a trend of moving from monolithic applications, which are applications composed of one single element, a big element which is in charge of our entire code, our entire business logic, our entire functionality, into microservices. Now, microservices are applications that are written in a way that they are formed of a lot of small components. Each of these components is in charge of one of our business logics, and these components speak with each other, whether synchronously or asynchronously, to form our application. Now, we call this a distributed system because, well, there's usually no centralized control, and each service can act on its own, and all the services together form our system. But you know microservices. Let's talk a bit about serverless. Now, I say serverless, most people, the first thing that comes to their mind is FaaS, or function as a service. Most cloud providers have a FaaS offering, whether it's AWS Lambda, Azure Functions, Google Cloud Functions, and the concept of all of these offerings is pretty similar. You take a chunk of code, you pack it up, you send it to the cloud provider, and then the cloud provider lets you configure various events, like an item put to a DB, or an item put to a queue, or maybe an HTTP request is made. So when these events occur, your code starts executing, and it can maybe return a response, maybe do some other computation. And what you do is you take a lot of these functions, you sign up each of them to a different event, and together they form your application. Now, the whole selling pitch of serverless is you don't have to set up any servers, right? It's very easy. There's no, you don't have to set up any servers. You don't have to set up any configuration. You just write your code, your own business logic, you deploy it, and you're done with it. So that's a great advantage, and we can see why it goes hand in hand with microservices. But when I'm talking about serverless, I'm not talking just about function as a service. Serverless is a way broader context, and it contains all the serverless ecosystem. Let's take Amazon's DynamoDB, for example. And I'm sorry, all my examples in this session is going to be about AWS. That's kind of my playground, but there are parallel solutions with other cloud providers. So let's take Amazon DynamoDB, for example. Amazon DynamoDB is completely serverless. It's a NoSQL database that Amazon offers. And in order to get started with it, you don't have to set up an EC2 cluster. You don't have to set up a server. You can simply create a table, say, this is my primary key, and you can start putting data into it. So when in this session I'm going to talk about serverless, I'm going to talk about function as a service, but we have to remember that it lives in the serverless context. Now let me just start off by saying that I think serverless is great. In this session, I will talk about why monitoring serverless applications might be hard and why it might be challenging, but it does not mean I think that serverless is not a good option or I discourage you from using it. The opposite way is the correct. We at Hexagon, which is where I work, use serverless all the time. Our entire backend is serverless, and we think it has some great advantages over the old way of developing software. For example, the development velocity can be much quicker, right? I can focus only on my product, only on my business logic. I don't have to focus on the infrastructure, and that makes me be able to iterate faster and release features faster. Other cool advantages that serverless has is, for example, auto-scaling, because I don't have to think about provisioning extra servers. It doesn't matter for me if I invoke one function or 1,000 functions. The cloud provider takes care of it. Now, of course, I have to design my system accordingly, but you get the idea that it's much easier in a serverless environment. Last, serverless is pay-per-use, which can be pretty significant cost saver, because you're actually paying for what you're using. You're not paying for your servers when they're idle. You're not paying for extra server you keep for a peak hour. You're paying for exactly what you're using your service for. So a little bit about me before we dive right in. My name is Gal Bashan. I've been with Hexagon for the last year, where we develop a serverless distributed tracing engine that is dedicated for serverless applications. Before that, I did some cool cybersecurity stuff at the IDF. And I live in Tel Aviv, Israel, which is way warmer than here. Really. So let's start by talking a bit about monitoring and why do we even need it? Because if we're talking about distributed tracing is a tool that enables us to monitor our application. And the first question that comes to mind is, why do we even need to monitor our application, right? So you're all probably monitoring your applications, and you know there are good reasons for that. And there are three key reasons that cause us to monitor our application. The first is we want to keep track of our system health. We want to make sure that our system is not only functioning, but is going to continue to function for the foreseeable future, that it's not going to have an error, and I'm not going to be woken up in the middle of the night trying to handle a crisis. The next thing that we monitor for is that when an error already occurs, we want to be able to troubleshoot and fix the error as fast as we can. This is called performing root cause analysis. Now, most people, when they think about monitoring, they think only about this part, but monitoring is actually much broader. The last thing about monitoring is that we monitor in order to get a good understanding of our system so we can optimize it. So we have a good observability of our system, and I swear this is the last time I'm going to use the word in this session. Not only observability, but really understand a system better and be able to optimize it. So let's tackle these one by one in a serverless context. So first, when we say we want to track our system health, in serverless, it's becoming quite ambiguous what our system really is. Because we don't have an EC2 instance or a server that we can just say, this, whatever's running on top of that, I have to monitor this, and if I monitor all of this, then I will for sure be able to keep track of the health of my entire application. Because our application is becoming distributed, and we don't really have a server, we first have to define what is our system, what do we have to monitor. So the first thing that comes to mind is that in order to monitor our entire application, we have to simply monitor all of our functions. And monitoring functions is important, right? It's basically our code. It is our business logic. All of the exceptions, all of the bugs will be there. And if we monitor our functions, we'll have a good understanding and a good ability to predict the behavior of our system. Now the question is that enough? And when we think of this question, I want us to remember that we're living in the era of APIs. When I say that we're living in the era of APIs, what I mean is that there are so many managed resources we can utilize. I mean, imagine me, let's say that I have a very successful blog site, and my core business value is giving the users an ability to read blog posts and valuable content. But one of the important things I need in my blog site is payment, right? I need subscription. But I'm not the only one that needs subscriptions. There are a lot of other applications that need subscription, that needs payment. So there was these guys at Stripe that said, all right, let's make a generic API for subscription. And whoever want to use it, it will be really easy to set up. And no one will have to think about how to create a complex payment system in their application again. So Stripe is just one example. We can think of Stripe for payment, Auth0 for authentication. We can even think of in-cloud providers like Amazon SCS for sending a mail, which is a relatively simple solution. It's simple action, but if you want to do it good, you should use a managed service. So what happens is we used all these managed services, and it can really help us focus on writing our own business logic and not writing generic stuff. But this also causes our application to become even more event-driven and highly distributed than it was before. Because we already had an application that is made of a bunch of Lambda functions that are invoked asynchronously by all kinds of different events. And now we're not only having the functions which are asynchronous, but they are also invoking different resources at different places, whether synchronously or asynchronously. And this is really making our system complicated. Now, here's an example of a serverless system. This is a famous example by Yang Pui, who is a very public figure in the serverless community. In this example, Jan took a monolithic application and converted it to a serverless application. And of course, we can see here that there are many lambdas. These are the orange squares, they are the lambdas. But there are also many other resources which are not the functions, not the lambdas. For example, we can see there are DynamoDB tables here. There are API gateways which can trigger a Lambda. There are SNSs, message brokers. There are even some solutions which in a different cloud providers, like Google BigQuery API or Twilio to send an SMS. And this picture makes it clear that our system is not just our functions. In fact, our system is bigger than our function. Our system our system consists of our functions, our APIs, and the different resources we use. And in order to be able to track the health of our system in a serverless environment, we gotta be able to track the health of all of these components. Because if Stripe has a problem, it's not only Stripe's problem, it's my problem, because users can't pay me. So we talked about what is the system and how we can track its health. Now, let's talk about what happens when we already had an error in our system. How can you troubleshoot and fix it effectively? So let's go back to an example. And we can, let's say that we know that an error occurred in this lambda. And we want to be able to find what went wrong in our application. Not just the actual exception that occurred, but to be able to find what is wrong with our application and how we can fix it. So we can start by searching in the monitoring tools of AWS, and maybe we can go to CloudWatch log, which is where you can see the lambda's output, and see all the different execution and all of the logs of the lambda. And then you can find the specific execution log and dive into it. But does that guarantee that we're going to be able to find the root cause of the problem? And the answer is absolutely not, because the problem might not even originate in this lambda. Because our system is very highly distributed, our problem might have originated 5 lambdas up the call stack, but it didn't blow up, it didn't raise an exception. It just threw malformed data down the call chain. Now this lambda got this data, couldn't handle it, exploded. Now great, we know that our lambda can't handle all of the input, and this is a really nice observation, but it does not mean that we know how to fix the problem in our system. So it is obvious that in order to troubleshoot and fix our system effectively, we cannot just look at a specific function invocation. We have to be able to track asynchronous events across our system. Now, these flows of data over asynchronous events is something that we call transactions. Now, there are different kinds of transactions. There are simple transactions, like the one you can see here in green, or whatever color that is, which consists of a really small amount of resources. But there are also more complex transactions, like the blue one, which is pretty long, the purple one, which branches off, right? There's a certain resource that invokes a couple of other resources, and now the transaction is branching off to multiple destinations. And we can also see the red one up the corner, where it's not only branching off, but actually a resource is revisited in the middle of the transaction. So the transaction, it has a pretty complex structure. Now the action of connecting this transaction together, piecing out the different events in order to create the transaction, is the action that we call distributed tracing. Now distributed tracing has been around for longer than serverless has been. It's been around for longer than microservices have been, probably. It's actually been around ever since we've had any kind of distributed system that we wanted to monitor. Now a transaction is basically a request or a flow of data within our system a request or a flow of data within our system. Now it's basically a directed acyclic graph of different events, where each event corresponds with a specific workload in this specific transaction. Now let's have a look at this example. We can easily piece out the transaction here, right? We know that one event is the client sending a message to the load balancer. Then there are a couple other events where the load balancer triggers 3 different services: the authentication service, the RPC, the billing service, and the resource service. Finally, the load balancer returns the response to the client. So let's say we collected all these events, we pieced them together, and now we want to be able to view this data. So there are usually 2 ways in which we show transactional data. The first is a timeline view, where we can see all the events next to one another, when each event is started, when each event ended, some basic data about the events, and this gives us a pretty good overview on our transaction. Now, this is the Jagger, which is an open source distributed engine, which you can use in order to set up distributed tracing for your application, and this is a Jagger UI because it's UI. Another common way to display transactions is a VI graph. Basically, we put all of our resources on a graph, and the arrows represents the different operations that took place. And that is it. And you can see some additional data on each event. Now, let's take an example of how root cause analysis should look like in a distributed system once you have distributed tracing. So this is again my blog site. A user can browse into the new post endpoint. This triggers the lambda that authenticates him. Then some data is sent to an SNS, which is a message broker between 2 lambdas. And then another lambda is invoked, and we're not really sure what it's doing because it has an error. But let's see if we can understand what went wrong in the system just by looking at the different traces that we got. So we can first look at the specific invocation of the lambda and see that he had a division by 0 error. Now that's not very informative because division by error can occur for various reasons. So we can go back to the SNS and see the actual data that was sent by it. So if we look in the SNS, we can see, for example, the topic and the content of the blog, but we also can see that the user in NA, which is pretty suspicious. I can go back and see the details of the specific execution of the previous lambda. which is really important because we can look at the CloudWatch logs of the specific Lambda invocation, and this way we can we can look at the specific CloudWatch logs of the specific Lambda invocation, and this way we can see that the user was not authenticated. I don't know if you can read the log from there, but the user failed to authenticate, but the message was still passed to the SNS. So it's pretty clear what's the bug in our system right now, right? Last, we can also see the request header that triggered this request in order to be able to reproduce this behavior and test it in our system to validate that after we made a fix, we can, for sure, the bug doesn't exist any longer. So let's talk about how we can implement distributed tracing in our application. So the first thing that comes to mind is that we can perform manual tracing. We can, before we use any resource of any kind, declare I am going to use this resource, I'm going to put this item in the DB, then I'm going to make the operation, I'm going to put the item in the DB, and finally I'm going to say now I'm done, I've finished putting all the items in the DB. Now this sounds pretty good. There's even a standard of how you should talk with the distributed tracing engine that's called Open Tracing that tells you how you should do it. But the problem with this approach is that it's really high maintenance, because we said that our system is very distributed, contains of many resources and many functions. So the act of doing this tracing can cost us a lot of time. Also, this approach is really risk-prone, because let's face it, everything that is left for a human will have problems in it, right? Now, that's not, I'm not saying this because I don't like humans, but because we all make mistakes. We forget to trace something, we trace the wrong thing, maybe we say it's not important enough, so let's not trace it. And what we end up with is not being able to understand our production environment. Now, when we talk about the serverless environment, this becomes even more critical, because serverless applications are very distributed. Complex application can have up to 1,000 of functions, and if we're gonna try and trace everything manually, we're gonna lose the development velocity, and that's why we went to serverless 4 in the first place. Also, serverless has some unique challenges which don't exist in other environments. Let's take timeouts, for example. When we deploy a Lambda or a function, it cannot execute forever. After a certain timeout, the cloud provider is going to throttle our execution, and what will happen is that our Lambda will be immediately stopped, no matter what it did. Now imagine that we were just sending a trace but didn't do the action, or maybe we're sending the trace in the end and we're going to lose all of our traces, or maybe we just didn't get to send the fact that we finished the operation. And again, what happens is that we don't have a good understanding of our production environment because we didn't take into consideration all of these limitations. Now the question is, what we can do, how we can leverage the fact that we're running in a serverless environment in order to make this process better. And the answer is, of course, automation. Because serverless is a really strongly defined environment. All of the APIs are commonly used. You're mostly going to use the APIs that are within your cloud provider, which are strongly defined. All of the event sources which can trigger your functions and all of the events that can happen are strongly defined. And the APIs which are not within your cloud provider are also strongly defined. So you can easily use automation in order to automate this process and maintain your development velocity while not losing the side of your production. Now the last thing I want to talk about is optimization. Now in serverless, optimization is really important because in serverless, time is money. Now it's not just a phrase that I'm saying. In serverless, time is actually money because it's based on a pay-per-use model. You're actually paying for each 100 milliseconds that or whatever bunch of time that the cloud provider decided that your function is executing. So let's see where we are actually spending our time. And this can usually be divided into two different buckets. First, we spend time executing our own code. Okay, so we spend our time executing our own code. This can be sometimes be optimized, sometimes it can be vastly optimized, but that's never going to be zero, right? Because if we have a product, if we're trying to deliver value, we're always going to have to do some computation of some kind. On the other hand, we have API calls. Basically, our compute units are triggering different APIs, and while they're waiting for their response, they're still executing, and we're still built for them. Now, I know at first sight it doesn't seem like that much, so I want to give you two examples of why it is so important to understand what your production environment really looks like, and not just what you think it looks like, and why you got to understand how your function is using the API calls. So the first example is a real-life example that happened to us in Hexagon. So let me set the scene a bit. In Hexagon, we're a monitoring company, and one of the features we provide is we monitor our clients' CloudWatch logs, which is where the Lambdas outputs their outputs their logs to. And we monitor their CloudWatch logs in order to be able to understand when a function began executing, when it stopped executing, if it had any errors. And this way we can provide some nice insights to our customers. So we said, all right, let's go and implement this feature, and let's do it in a serverless and cool way, and let's try to write as less code as possible and use as many resources as we can. So the solution we came up with is this. First, let's have a lambda, the middle's lambda over here. That's all it can do. It can read one client-specific lambda's CloudWatch log, analyze all the invocation, and parse the data and store it. Then we'll have another lambda that all it does is invoking the lambda that we just talked about for each and every of our clients' lambdas. Now that sounds like a really serverless solution, right? Because it has really little code. Each of these lambdas are less than 100 lines of code. And it sounds like it's going to autoscale pretty good, right? Because it doesn't matter if I'm invoking 1 function, 100 function, or 1,000 function. It should always play the same. So we were really happy with ourselves and went along. But then one day, now this is an actual message sent from my CEO to my CTO. And I know you can't read it because it's in Hebrew, so I'm going to translate it for you. It's basically my CEO asking, is this for real? What happened is that my CEO logged into our monitoring platform. We use our monitoring platform to monitor our monitoring platform. He logged into our monitoring platform, and what he saw is that the estimated cost of one of our lambdas is $1,200. $12,000. So this is a lot to pay for a lambda, especially for a young startup, and even for a high-scale lambda, this is a lot of money. So of course, panic was spreading, and we started to try to understand what was going on and what was the root problem with our code. And this is what we discovered. Now, the thing we forgot to pay attention to is one of the serverless environment restrictions. And in this specific case, it's a restriction of CloudWatch logs. Now, CloudWatch log is a really nice service, and this is me being really polite here, but let's say CloudWatch log is a really nice service, but it has a really low throttling limit. What happens is that you can make 5 requests to CloudWatch logs, and after 5 requests, you're going to be throttled, and you can resume requests only after a second has passed. So let's try to think about what happens when we have a client that has 500 Lambda functions. So we spawn 500 Lambda functions to monitor his 500 Lambda functions. These 500 Lambda functions begin executing and access CloudWatch logs. 5 of them succeed to read the first part of the log. 495 of them fails and wait for another second. And what we end up with is around 5K concurrent Lambdas executing for almost 5 minutes every 5 minutes. And this is costing us a lot and lots of money. Now, the funny thing about this story is that there really is no error in this scenario, right? Because we handled CloudWatch errors because we knew that there might be a retry, so we just implemented the retry mechanism. And there was no error, there was no timeout because we caught it before the functions were timing out. But we were going to pay a lot of money because we didn't have a good understanding of how our production environment really behaves and not just how we think it behaves. Now, the next example is a quick one. This is again my blog site. This time you can see the full transaction which doesn't have an error. So again, the user can browse to /new post. He's been authenticated with the Lambda. Then some data is passed along via the SNS message broker to the next Lambda. And the blog post is stored to the DB, and an SMS is sent to the API author that a post was submitted and is going to be published soon. Now let's have a deeper look in this transaction. And we can see that authenticating the user is taking 700 milliseconds. Now I know 700 milliseconds doesn't sound like a lot of time, but this entire transaction end-to-end is taking only 1 second. And each operation in it is taking less than 100 or 150 milliseconds. So we're basically spending 70% of our time authenticating user, using an external API. And this might not be so bad if we're using it once or twice a month, if this pattern is being invoked. But if it's being invoked 1 billion times a month, then we're spending 70% of our money on waiting for auth 0. Now, it's not like there are no easy solutions, right? maybe we can move closer to Auth0 geographically, or maybe we can switch a service, switch to Cognito, which is the identity provider of AWS, to stay within our own cloud provider. But in order to be able to fix the problem, we first have to understand that the problem exists. Now this leads me to business flows. This leads me to business flows. What is a business flow? A business flow is a pattern that repeats itself in our application, a transaction that several transactions that share the same pattern over and over again. So let's take a look at two business flows in our application. First, we have the business flow of a user reading a post. The user can browse to the reading post endpoint, then it's being authenticated, then the post is brought up to the DB and sent to the client. Now, it doesn't matter which user was authenticated. It doesn't matter if the post was about spuds or it was about serverless. What really matters is that the pattern always stays the same. Same thing goes for submitting a post. The user can browse to the submit post endpoint, then it's again being authenticated. The post is sent to the DB and sent along for further processing. But again, doesn't matter which user was authenticated. It doesn't matter which post he wrote. All that matters is the pattern stays the same. Now we can take all these transactions that fit the same pattern, call them a business flow, and look at them over time. And this way, we can get a really good understanding of our production environment. Because in the previous example, where we took a look at the transaction where authenticating the user took about 700 milliseconds, if we take a look at a single transaction, we can never be sure there's a real problem. Because we just might have caught Auth0 on a bad second, where it took us a lot of time to authenticate, but usually communication with Auth0 is taking less than 1 millisecond. So in order to be sure that we are addressing the right pain points in our application, we have to look at the business flows over time. So this is an example of all the business flows in our application, and we can have a look, and this will help us understand the problem with our application. So we can have a look at the business flow that is taking the longest, and we can take a look at all of the components that make it. And we can say, we can have a look at each and every operation over time in all of the transactions to understand where is our pain point and how we can fix them. And if we didn't have this understanding, we wouldn't even have, we weren't even being able to approach optimizing our system. So let's sum up. We talked about that in order to track our system health in a serverless environment, we have to define first what is our environment and what is our system. And it's not enough just to keep track of our functions, but we have to keep track of all of the resources we're using. Next, we talked about that in order to perform effective root cause analysis, we have to use distributed tracing. And in order to do it good in a serverless environment, we have to use automated distributed tracing. And last, we talked about that in order to optimize our system, we gotta have a good understanding of our system. We can't just look at a single transaction, but we have to look at business flows across time and how they behave, and only this way we can find the real pain points in our application. Thank you very much. I hope you liked it, and that is it.
Thank you very much, Gal. We have time for one quick question, if anyone has one. John?
How did you solve your authentication wait time in your Lambda?
The authentication or the one with the...
You're waiting for 700 milliseconds.
So basically there are easy solutions, right? Because you're gonna wait for some time, right? It's never gonna be zero probably. But you can, for example, move to a region that is closer to Auth0. What happened here is that I ran this application, I think, in Ireland, and Auth0 is working on America, and this was a pretty long distance. So I just moved my application to ESS1, for example, and this really improved the timing. Another thing you can do is consider switching to a different provider, right? If Auth0 is giving you a problem, you can just use Cognito, which I tested like within AWS clouds take like 20 milliseconds for each request. So there are solutions. It's probably never going to be zero, although there are APIs that you can invoke asynchronously and maybe have them invoke a different Lambda as a response, but you can improve much more than 700 milliseconds.
All right, I'm afraid that is all the time we have for questions at the moment. Gal's going to be around all day, I think. Yep. So can we thank our speaker again?
Thank you very much.